In this problem, we're given a three-dimensional state of stress. We're given sigma x, sigma y, sigma z, and the three components of strain, tau xy, tau xz, and tau yz. We're given that the material is steel, so we know the Young's modulus E, the Poisson's ratio there of nu. We want to calculate the state of strain. There'll be 6 components. So what we're going to do is just use the 3D equations that we derived here in lecture. Let's begin with the x component of the strain, sigma x. So that's going to be 1 over the Young's modulus 1 over E times the quantity sigma x minus nu times the sum of sigma y and sigma z. The Young's modulus is given to us in gigapascals, so we'll convert that to pascals. That will become 210 times 10 to the 9th Newton per meter squared. The stresses are given to us in megapascals, so I'll write the mega part on the outside. This is 60 times nu, which was 0.3, times 20 plus 30. And the factor on the end, again, represents the conversion from megapascals to pascals. That's 10 to the 6th newtons per meter squared. So when we do our calculations, we end up with the ratio here of 52.5 divided by 210 times 10 to the minus 3. Recall that strain is a dimensionless amount. Epsilon y. The equation for that is 1 over the Young's modulus, sigma y minus nu sigma x plus sigma z. I put in the numbers for that. That becomes 1 over 210. You have 20 minus 0.3, 60 plus 30. And on the outside, I have something which is 10 to the minus 3, because that's going to be that conversion factor from megapascals divided by the conversion to gigapascals. So this number becomes a minus 1 over 30 times 10 to the minus 3. Sigma z. The equation for that was 1 over E, sigma z minus nu sigma x plus sigma y. So that becomes 1 over 210. The sigma z was 30 megapascals, minus the 0.3 Poisson's ratio, the 60 for sigma x, the 20 for sigma y, with the conversion of 10 to the minus 3 on the outside. Again, the ratio of the conversion for megapascals divided by that for gigapascals, and this becomes 6 over 210 times 10 to the minus 3. Please note that this is a plus, this is a minus, and this is a plus. So in the x and z directions, we're looking at positive strains. In the y direction, it's a compressive strain. In order to find the shear strains, we first need to find the shear modulus G. We know E and we know nu, and so we take E divided by 2 times the quantity 1 plus nu, so that's 210 times 10 to the 9th in pascals, divided by 2 times 1.3. So whatever number that comes out to be, when we get through to find the shear strain of of gamma xy, that becomes tau xy divided by G. So we have numbers for that. Gamma xz is going to be tau xz divided by G. And gamma zy, or yz, whichever way that you want to write that, divided by g, that gives us the last component. So this problem is an exercise really in getting used to those 6 equations. The first 3 being the relationships between the normal stresses and the normal strains, and then secondly, the shear stresses to convert to shear strains. Keep in mind that the shear strains are related by the shear modulus G, which it in turn is related back to the Young's modulus E and nu by this equation here.